I'm Professor Rad, and this is Precalc video 214, graphing rational functions. So it's pretty self-explanatory. We're going to take all of the techniques we've developed so far for both polynomials and rational functions and use them to graph rational functions. So let's talk about these steps. I'm going to step out of the way in case you want to pause the video here to copy these down. And now let's go through them. So as with polynomial functions, these steps are general guidelines. You don't have to do them in this particular order, but they are good things for us to find when we go to graph. So the first thing you want to do is factor the numerator and the denominator. So as we saw in some of the previous videos, having either the numerator or the denominator in factored form is going to help us identify certain features, like where there might be a hole or where there might be an asymptote or even the x-intercepts. So sometimes you want your rational function in factored form. Other times you may want it all multiplied out. So for example, when we found our oblique asymptote in the last video, we needed the numerator and the denominator in their expanded forms so that we could carry out the long division. So whichever format your rational function's in, you kind of want both of them. You kind of want it in factored and also in like expanded format. You also want to make sure you state the domain here so you can kind of do a check at the end to make sure you haven't plotted points where you shouldn't be plotting points. Number two, we're going to simplify. So now that you've got everything factored, we're going to cross out those common factors, bearing in mind that those common factors we crossed out are where the holes are going to be. So if you simplify and you end up with a polynomial function, you're actually like almost done. So in that case, like let's say you factor it and you get something to cancel and you end up with a quadratic. That means now you get to graph that parabola, and all you have to do is figure out where that hole is and just graph an open circle there for that hole and you're done. Otherwise, if you cancel out common factors and it doesn't reduce to a polynomial, it's still in its fraction-y form, then you have to make a note of where those holes are and then carry on to these next steps. So number three is we want to find and plot the x-intercepts. So remember our shortcut for that is you want the simplified numerator equal to 0, and you solve that. So so that's a shortcut for how we can find our x-intercepts. Then we want to find and plot the y-intercept. So you can find the y-intercept by finding f of 0. And so you just plug 0 in, see what you get. Now you might have a vertical asymptote at f of 0, so 0 might not work, or you might have a hole there or something like that. That's okay. If you can find it, find it. Then you're going to find and graph the vertical asymptotes. So remember, your vertical asymptotes are where your simplified denominator is equal to 0. So notice for all these things, we've got 0 involved already. So for your vertical asymptotes, that's when your simplified denominator is 0. For your horizontal or oblique asymptotes, remember if it's a proper rational function, then you have a horizontal asymptote of y equals 0. And if it's improper, we're going to do long division or synthetic division if the opportunity arises, and we ignore any remainders that we get. Then we're going to make a table of signs. So we did this with polynomials as well to see where it crossed over the x-axis, so where it turned from being negative to positive and so on. When we make a table of signs for rational functions, we actually have two things we have to check. So when you create your table of signs, you're going to use your x-intercepts, just like we did for polynomials, but also the vertical asymptotes. This is because the vertical asymptote is another place where your rational function, maybe it's like going down to 0 on one side, and then it's like super big positive on the other side of that vertical asymptote. So that's one other place where we can change signs. And lastly, we finish graphing. That's all. We just finish graphing it. So you will use your table of signs and any additional points that you choose to find to help you graph. So these examples can be a little bit long and labor intensive. So let's not dilly-dally, let's get going right away with our first example. Alrighty, so to help us do these examples, I've got a really summarized version of my steps written over here on the side. And for this first example, we're going to analyze and graph r of x, which is equal to x cubed minus 2x squared minus 15x, all over x minus 5. And I've got some graphing space here to help me do my graphing later. So if I look at my steps, our first step is to factor and identify the domain. So let's go ahead and do that. So my denominator is already in factored form. That's really nice. For the numerator, I notice that each term has a factor of x. So I'm going to factor that out first. And that will give me x times x squared minus 2x minus 15. And then I think this is going to factor because -5 and 3 multiply to -15 and add to -2. So I have x times x minus 5 and x plus 3. And this is all going to be over x minus 5. So that's my first step, is doing the factoring. And for my domain, remember the domain, the denominator can't be 0. So I'm just going to put a note here for the domain. X cannot equal 5, because if we had 5 here, we would end up with 0. Cool. That's step 1. Step 2, we want to simplify and then identify any holes if we have them. So we do actually have a common factor in the bottom and in the top. So we can cancel those out and we get x times x plus 3. Now this, my friends, is excellent news because it means we've simplified to be a polynomial, so we can just graph this polynomial. We don't have to worry about any of the other steps. So we just have to figure out where that hole is going to be because of this canceled factor, and then we can jump to graphing. So to figure out where that hole is, we're going to substitute in, because we canceled x minus 5, we're going to substitute 5 in, that's the piece that's forbidden from our domain, into the simplified form. So I'm going to do 5 times 5 plus 3. So 5 and 3 makes 8, and 8 times 5 is 40. So that means I have a hole when x is 5 and when y is 40. So I can go ahead and plot that point now, so I don't have to worry about it later. So 5, 40, and it's going to be all the way up here. And I'm just going to graph it as an open circle. Now I plot this polynomial. Now I recognize x times x plus 3. That's going to be x squared plus 3x, right? If I were to distribute that out, and that's a quadratic function. So I can put this in vertex form if I want and use that to graph. I think I'm just going to use my x-intercepts, which are going to be at 0 and -3 because of those two factors. I'm going to use those, and then I'll use some symmetry to finish graphing. So here's what I'm doing here. I've got x equals 0 and x plus 3 is 0. That means x is -3. So these are where my two x-intercepts are going to be, one at 0 and the other one here at -3. And then, let's see, from 0 to 5 is 5 spaces. So 1, 2, 3, 4, 5. If I went down to -8, I could plot a point up at 40. So I'm nice and symmetric with that point there. And then I can connect those and graph my function. So nice and smooth and continuous parabola here, except for this teeny tiny microscopic little hole. And that's it. That's our graph of our function. So this example was a little bit of a cheat because we got through step 2. I mean, we kind of did a little bit of the intercepts, but really for a rational function, we didn't get through the whole, bulk of the steps. So let's do a problem where we don't have like something easy happening. Let's do something more long. This time we're going to be analyzing and graphing the function f of x, which is x cubed minus 1 over x squared minus 3x minus 10. So for this one, first we're going to factor and then find the domain. So I recognize the numerator as a difference of perfect cubes. It is x cubed minus 1 cubed. So when I go to factor that, I'm going to get x minus 1. Because I keep this, I just drop that cubed part. Then I'm going to square the first, so x squared. Multiply these two, 1 times x is x. Square the second, so that's 1. This piece is always positive, and then this one has the opposite sign, so we get a plus here. Now, when I have this, I believe this is going to be a prime quadratic because nothing multiplies to 1 and adds to 1. So I can't factor that quadratic anymore. I can factor the denominator of this rational function though. So I think -5 and +2 will multiply to -10 and add to -3. So that's how I'm going to factor this denominator. Right, so that's the factored form of my rational expression. And we also need to state the domain. So to state the domain, I need to make sure that x is not 5, because 5 minus 5 would be 0. And x can't be -2 because -2 plus 2 would also be 0. So for my domain, I'm going to get all the x's that are not equal to 5 or -2. Step 1 is done. Step 2 is also done, actually. There are no common factors between the top and the bottom, so there's no simplifying needed to be done, and there are no holes. So that one's all good to go. For 3, we want to find the x-intercept by setting the top equal to 0. So I'm going to set x minus 1 equal to 0. I don't know why I put parentheses around that. So I'm going to set each of these factors equal to 0, and x squared plus x plus 1 equal to 0. So from this one, I know that x is going to be 1. And I actually don't have to carry on with this one. If I find the discriminant, which is b squared minus 4ac, that will give me 1 squared minus 4 times 1 times 1. So 1 minus 4 is a -3. Because the discriminant is -3, that means there are no real solutions to this. So I'm not going to get any real x-intercepts from that. I'm just going to get complex values. So this one has no real solutions. So what that means is this function only has one x-intercept, and it happens when x is 1. So we're going to have an x-intercept of 1, 0. Good. All right, let's see what happens next. Next, we need the y-intercept. So we're just going to sub 0 in for x. I usually find the original format to be a little bit easier for that, but you could do either the original or the factored. So I'm going to do 0 cubed minus 1 over 0 squared minus 3 times 0, which is 0, minus 10. So this will simplify to be 1/10. Ooh, so that's a teeny tiny y-intercept. So our y-intercept is going to be the point 0, 1/10. Next, we need our vertical asymptotes. This is going to happen when the bottom is equal to 0. So if I set x minus 5 equal to 0, I get an asymptote of x equals 5. So I'm going to put my vertical asymptotes are going to be x equals 5. And if I set x plus 2 equal to 0, that means x is going to equal -2. All right, found our vertical asymptotes. Next, horizontal or oblique. So this is going to be 0 if we have a proper rational function, which we don't. So the degree of our numerator is bigger than the degree of our denominator. So we don't have a rational or a proper rational function. So that means we're going to have to do some division. So let's divide. Now x cubed minus 1, I see that I'm missing a squared term. So 0 squared, or 0x squared plus 0x. and then minus 1 at the end. And then I'll put my divisor out here. And I'm just going to zip through the dividing here. So if you want to practice and pause and then unpause and see if we get the same thing, that would be a good plan for practicing. All right, so we did our long division, and remember when you do your division, you can ignore the remainder, so I don't care so much about the remainder. I've got, excuse me, I've got x plus 3 left up top. So that's going to be my oblique asymptote in this case. So oblique, we have x plus 3. Okay, next we need a table of signs. So our table of signs is going to be made by using the x-intercepts and the vertical asymptotes. So because we have one x-intercept and we have 2 vertical asymptotes, we're going to have 3 spots on our table of signs. Now, in this case, well, first we want to make sure they're in order. So we have -2, 1, and then 5. And when I make my table of signs, because I'm going to be referencing this when I go to graph, actually, I'm going to make it a little bit smaller so it's easier to see when I graph later. Because I'm going to be graphing over there, I think. So here's my -2, 1, and 5. What I like to do is give myself little notes here on the table of signs, what's happening at each of these values. So I have an x-intercept at 1, 0. So I'm going to plot 1 there, a point there. And then I have asymptotes at those other 2 places. So I'm going to indicate that by doing like a little mini asymptote there. So when I go to graph, I know that that's what's happening. Now, with polynomial functions, we had some idea about what was going to be happening, whether we had a turning point or that sort of information, whether it's going to go up on one side, down on the other, that kind of thing. We don't have that here. So I'm going to show you kind of a little, well, it's not really a shortcut in this case. We're just going to do the best we can do. I know that my y-intercept is positive because of 1/10. So between -2 and 1, that's when x is 0. The y value is going to be positive. Now I have to figure out the rest of the stuff. So what I'm going to do is I'm going to pick a number between 1 and 5, let's say 2. So I'm going to throw 2 up into, well, I'm not going to throw it up, oof, but I'm going to put 2 into the function over here. So I'm going to have 2 cubed minus 1 over 2 squared minus 3 times 2 minus 10. Now, when I do this calculation, I don't really need to know the number of my answer. I just need to know the sign of my answer. So 2 cubed minus 1 is a positive, right? Because 8 minus 1 is positive. Then this looks like 4 minus 6 minus 10. That's going to be a negative number because I have 4 minus some bigger stuff. So if I have a positive over a negative, that's going to give me a negative on this interval. Now, if you want to go ahead and solve this and find the exact value, that's totally fine. But all we really need for our table of signs is whether it's positive or negative. So I'm going to pick a number bigger than 5 to see what's happening to the right of 5. So let's say 6. So 6 cubed minus 1. 6 squared is 36. 6 times 3 is 18 minus 10. 6 cubed minus 1 is definitely positive. 36 minus 18 is 18. Minus 10 is positive 8. And positive over positive is going to give us a positive. Nice, we're almost done. Now we just have to figure out what's happening before -2. So maybe let's say -3. So -3 cubed minus 1. And then we have -3 squared, which is 9. Minus 3 times negative 3 is plus 9, minus 10. So now if I cube a negative, I'm going to get a negative number. So a negative minus 1 is going to be negative. And then 18 minus 10 is a positive. So because we have negative over positive, we're going to end up with a negative here for our answer. So that's how you can create your table of signs without finding, exact values. You can just kind of figure out what the sign of the top is and the sign of the bottom is. That's typically a lot easier in factored form, except we have this quadratic here, so it wasn't going to be super helpful in this case to use the factored form. But you can also use relationships about like if you're multiplying negatives and positives and things like that. But also if you're more comfortable just evaluating the point, feel free to do that too. So we made our table of signs, now we just graph. So let's graph. I'm going to clear out some space here for me to sketch this function. So I'm going to clear this out here. Now, when you go to create your horizontal and your vertical axis, it could take a little bit of trial and error. So to set us up on this one, I'm just going to tell you what I found. So I found that I needed to go from about like -8 to +8 on the x-axis. And then I needed a little bit of negative space on the vertical axis, but a lot more positive space. So my vertical axis is going to go from, it looks like -8 up to 16 or so. So let's go ahead and see if we can do that. So 2, 4, 6, 8, -2, 4, 6, -8. I'm going to count by each tick mark is 2 this time, so 2, 4, -8, 4, 8, 12, 16, 20. All right. So once you have your x and y axes set, you want to start out by plotting all the points you know and by all of the asymptotes that you know. So let's go ahead and plot the points we know first. So we have the point 1, 0 and the point 0, 1/10. So 1, 0, 0, 1/10 is going to be itty bitty. So probably like right there, just above the axis. Next, let's go ahead and graph our asymptotes. So we have 2 vertical asymptotes, one at -2 and one at 5. So let's go ahead and graph this one at 5. And this one here at -2. And then we also have an oblique asymptote at x + 3. So that means this asymptote has a y-intercept at 0, 3, and it has a slope of 1. So we can use that to graph that line. So 3 is halfway between 2 and 4 here. And then I'm going to go up 1 and over 1. So up 1, over 1. I got to be careful because my scale is different on my 2 axes. So just be careful with that. All right, so since I drew my axes kind of freehand on the board, it's not really perfect, but we're gonna do our best here. And then we connect the points as we can. So we know that between 1 and -2, that our x values are going to be positive. So what that means is from this point over to this vertical asymptote, I'm going to be above the x-axis. So I can kind of sketch in that I'm going to be doing something like this here. And then from 1 to 5, it's negative. So that means it's going to be below the x-axis between when x is 1 and 5. So we've got something like that going on. So notice that this is a place where our function is crossing its oblique asymptote. That's because this is happening in the middle of the function. We're going to use this oblique asymptote for stuff happening on the right and for stuff happening on the left. Now, before I move on, you do want to consider what's happening with your asymptotes and how they interact and how your function will interact with them. For example, think of the asymptote as dividing each of these sides into 2 pieces. So I have this lower piece where my function is going to be between this oblique asymptote and the vertical asymptote. So if my function is negative, I'm going to stay under here. If my function is positive, 2 things. I'm going to need another x-intercept, because if it's positive, it's going to start out here, and then at some point it will have to cross the x-axis to get closer and closer to that oblique asymptote. So you want to use your table of signs carefully to see whether you're like in the bottom portion or in the top portion in this like division. So in this case, we had a negative. So that means I'm stuck in this bottom portion. I'm never going to be able to go back up above the x-axis. So that means I have a little piece over here that's going to come up. And then as it bends, it's going to get closer to that line. Similarly, when I look at what's happening over here, we have positive values to the right of 5. So if I look at how the asymptotes are dividing this space, we have one section that's up here. And then we have another section that's below underneath here. So see how this below portion is going to end up crossing this x-axis at some point. So if I started up here, I'm going to have to cross the x-axis so that I have this negative asymptote. So we can't do that because we don't have any x-intercepts bigger than 5. So we're going to be stuck in the top portion up here, which matches our positive that we found here. So this piece is going to go closer to this line as I go to the right, and then it's going to curve and go up here at the vertical asymptote. So we get closer here, and then our vertical asymptote like that. So this is our quick sketch of, right? This is our quick sketch of this function. If you want a little bit more precision in your graph, you can find a point either for down here or for up here to give you additional guidance. So if I wanted to substitute 6 in and find the actual value, that would give me a y value. But in my classes, what I look for is, do you have this middle piece where we usually have more detail? Do you have that part figured out? Are your asymptotes correct? And is the piece of the function in the correct like little quadrant or little section divided by the vertical asymptotes and the oblique asymptotes? So that's going to conclude our graphing of rational functions. In the next video, we're going to take kind of a little bit of a turn and take a little break from all this intensity and look at just combining algebraically different functions. And we'll see how you can combine functions algebraically. So I'm looking forward to seeing you in that next video. I hope, I know this was an intense video, but I hope it helped with our graphing of rational functions. And I look forward to seeing you in the future. So bye for now.